In this video, we're going to talk about numeration systems. So these are systems of numbers, in particular held by some of our ancient cultures here that we've studied. I'm going to call this section 3.1a because in the next video, I call it 3.1b. And we're going to focus on four number systems in this video, and we'll start with the Egyptian numeration system. Now, we are going to have to draw these, and you can find the book's version of the drawings on page 85. But you're going to have to draw them in the homework, so might as well kind of practice now. Okay, so the first number we're going to introduce a symbol for is the number 1,000,000. And this one looks like a person that is astonished. Okay. The number 100,000 is represented by a tadpole. I don't think that's supposed to be crossed. I think it's just supposed to meet together. There we go. The number 10,000 is a pointing finger. Number 1,000 is represented by a flower. In particular, I think it's called the lotus flower. Yeah, it is. And it's got like a little base, something like that. 100 is represented by like a spiral, like this, which I believe for them was the rope. Then we have the number, here, let me scooch a smidge. Number 10 is like an upside down U, which is supposed to represent the heel. And then the number 1 is a single slash, which is supposed to be a stick. Okay, so there you go, the Egyptian numeration system. So each of these symbols represents its weight as that. So 2 astonished men, this first category, I think that's what they call it, the astonished man, is 2,000,000. Okay, and that's what that represents. So let me go ahead and give an example. Let's say we wanted to write the number 2,342 using this system. Okay, so the first thing we would do is we would start with 2 1,000s, which are 2 of those flowers. All right, and another one. And there are variations on this system. Like if you look online, they might draw them a little bit different. It kind of depended on the person too. All right. 3 100s, because we have 3 in the hundreds place. So I'll do 3 of these spirals, which are the rope. 4 10s, so 4 upside down U's, and then 2 sticks. And there you go. That's how you'd represent the number 2,342. Okay. Now let's look at the number 10,125. So for this, we're going to have to use the pointing finger. So sad. And then nothing in the thousands place, right? Because it's 10,000 only. Then we need to go to hundreds. So 1 spiral, 2 20s, and then 5 ones. And there you go. That's how we represent that number. Okay, so that is the Egyptian numeration system. The second system you've probably had some familiarity with, and that's the Roman numeration system. This is also, by the way, I wanted to mention this for even the Egyptian one. All of the numbers we're working with are powers of 10, right? So this is 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, meaning literally I'm talking about an exponent, okay? That means that this number system is base 10. And the Roman numeral number system is also base 10. And that actually makes it a little bit easier on us that we're working with base 10 because that's what we're familiar with. Okay, so let me go ahead and draw out the Roman numeration system. So the number 1 is represented with an I. The number 5 is with a V. I like to kind of put the bar on cross to help me. 10 is an X. 50 is an L. 100 is C. 500 is D. And 1,000, oops, 1,000 is M. Okay, so that's the Roman numeral system. Now, the Roman numeral system uses a subtraction version as well, a subtraction. Oh, that's supposed to be a C. A subtraction representation as well. It could be done both ways, okay? So let me give an example of what I mean by the subtraction system. So the number 9, for example, can be represented two different ways. If I wanted to use the subtraction system, what I would do is I'd take the number 10 and subtract 1 from it. And in order to subtract 1 from it, I put a 1 in front of it. So that represents the number 9. It is possible to do it without the subtraction system. With that, you would start with the V, and then you would put the 4 ones afterward. And that's how you represent 9 as well. The advantage of the subtraction system is it can go quickly, but the disadvantage is when we start working with very large numbers, it can be really cumbersome. So often with larger numbers, we tend to stick with the standard, just kind of writing it out using the smallest version of the number and building up. Okay. Here, let me do another example. Let's represent 40 two different ways. So let's do it with the subtraction and then on subtraction. Okay, so with the subtraction, 40 is close to 50, right? So I would go ahead and start with 50. And then I want to subtract 10. So I'd want to put the X in front. So basically it looks like XL. Actually, I don't think you want to put the bar over the the L. So it doesn't look like a 1. Oh, oops, sorry. And you want it in front. Wow, I just finished saying that. Okay, so there you go. The subtraction system, you put the number you're subtracting in front. Oh, no, I had it in front. Sorry, L is the 50. I did that right. Okay, second guessing myself. The non-subtraction system means that I would use 10 4 times. So I would do 1, 2, 3, 4 X's. Okay, so there's the two systems for Roman numerals, just being aware that some of them are written in subtraction whenever the smaller number is written in front of the larger number. Okay, that's when we see the subtraction system. So let me make a note of that. Smaller number in front of larger number. Okay, here, let's do one large number. Let's do the number we did earlier, 2,342. Okay, so for this one, we would do, okay, so 2,000 means that we would need M twice. And then 300 would be 3 C's. 40 would be 2 X's. I'm sorry, 4 X's. And then 2 would be 2 I's. And there you go. There's that number there. Okay. The Babylonian numeration system. So this is the third system. And for the first time, we're going to see something that is not base 10. The Babylonian system is actually base 60. We'll use two primary numbers to do this. The number 10, which is it's supposed to be like a bow for a bow and arrow. All right. And then this number, the number 1, which is represented by, I think it's supposed to be a cup, something like that. Okay. I don't quite remember. Sorry about that. Okay, let's look at some examples. Let's do the number 47. Okay. So 47 is going to be just like we kind of did before, 4 bows. Oops. And you can stack them. They don't have to go in a row. You can stack them. 4 bows and 7 of these cups. So here, I'll stack these as well. You don't have to go in a row. You can go in a row too. That's fine. Nothing wrong with that. But they often do stacking too to fit it into smaller spaces. Okay. Now 47 is a little uninteresting because this thing is base 60. And that means that they build numbers a little bit different. Let me give you an example of what a number could look like that's bigger than 60 and how it would kind of look to us. Okay, so here, I'm going to give you the number itself in Babylonian. So we have 4 bows, 1 cup, another bow, and 3 cups. Okay. So we're kind of thinking of this as 2 different numbers. And I mean, we're able to kind of see that because they repeated the bows, right? So you can kind of tell that one number has 4 bows, the other number has 1 bow. So we can somewhat see that in the fact that they had bows twice. Okay. The number itself it has like a place value. So the first number, and when I'm referring to the first number, I'm referring to this one, the left number. I'm sorry, the right number. This right number is like in the ones place, kind of like our right number is in the ones place. Okay. And the number that they are using to represent there is the number 13. Okay. But the second number is in the next place up, which for the Babylonians is the 60s place. That's why it's base 60. All right. And the number 41 is there. Okay. So to actually see what this number is in our system, we're going to multiply 41 times 60 plus 13. Grab your calculator and you should get 2,473. If I did that right. Okay. Let's try another one. Let's try bows, 2 bows, 2 cups, 3 cups, and 3 bows. Okay. So starting with the ones place, which is all the way on the right. Okay. 3 bows would be 30 in the ones place. Now in the 60s place would be the number 3, 3 cups. So the number 3. And then in the 60 squareds place, we have the number 22. Okay, now we'll multiply that out to figure out what the number is in our number system. But I want to pause for a second and I want to come back up to the top because I kind of rushed over the discussion about our base number system, base 10 number system, when I kind of talked about the Egyptian number system. But I want us to kind of see it now. So when the ones place is 10 to the 0, I said that. The tens place is 10 to the 1. This is 10 squared, 10 cubed. That's how our number system is built. Powers of 10. Okay, this is 10 to the 6. All right. But the Babylonian system built it up by 60s. Okay, so they go up by 60, 60 to the 1, 60 squared, 60 cubed. That's what the other base number systems mean. It means that each place value represents the base raised to the exponent. Okay, that's how the base number systems work. So in the Babylonian, being 60 means that each one is multiplying by 60 each time. So we have 60 squared. If we were to have one more number, it'd be 60 cubed. Okay. Now, real quick, I do want to comment that 60 squared is 3,600. That might be useful for us. Okay, so go ahead, multiply that on your calculator. Tell me what you get. I got 79,410. All right. Now let's go the other way. Now here's where we actually have a challenge because we can no longer think of it in our base number system. We have to think of it in their base number system. So like if I wanted to represent the number 10,821 in the Babylonian system, I need to think base 60, okay? So the first thing I need to do is I need to think about how many of each place value fit. So I usually start with the biggest one I can. So in this case, 60 squared would probably work for us. In other words, I'm trying to figure out how many 60 squareds fit into 10,000. Or another way of saying that is how many 3600s fit into 10,000. Okay. And I'm going to guess, I'm going to take 3,600. I'm going to times it by 3 because I'm thinking 3 times 3 is 9. So 9,000. Ah, okay. So that works. So if you take 3 and times it by 3,600, just so you know, you would get 10,800. Okay. That's what's already accounted for. Here, I'm going to put it down below in green, 10,800. Okay. Plus, all right. So I have 21 left over. 21 left over. So I'm going to skip the 60 slot. Okay. Basically, there's a 0 there, quote unquote. And I'm going to go down to the ones place. And in the ones place, I'd like the number 21. Okay, in the ones place. So here's how that's going to look when I draw it out. So a 3 in the 60 squared place would be 3 cups. And then 21 in the ones place is going to look like 2 bows, 1 cup. Now here's where we finally see a problem with the Babylonian system. They don't have a 0. So when somebody looks at this number, right, they see it on the side of the wall or something like that, you might think that this is in the ones place and this is in the 60s place, but this is actually supposed to be in the 60 squared place. Okay, so it is a problem with the Babylonian system. So note, the Babylonians do not have a 0. 0. And the reason that matters is a 0 is like a placeholder. It says to somebody that we're skipping a place value, and therefore that's why there's a 0 here. And that is kind of hard for the Babylonians. They didn't quite think that one through. Okay, but the next number system does think it through. The Mayans. The Mayans do have a 0. And the Mayan numeration is actually base 20. Okay. Now in the book, they do have like all the numbers from 1 to 19 on page 87. Just if you want to go reference that. I kind of remember 3 of the numbers to kind of help me do this. The number 0 is, I believe it's a loaf, like a loaf of bread. The number 1 is a dot, and the number 5 is a horizontal line. Okay, so let me kind of give an example of what a number is going to look like, because there's a stacking system with the Mayan numeration. So the number 7 is going to look like a bar with 2 dots on top. So the 5 with 2 ones. The number 13 is going to look like 2 5s and 3 ones. And then like the number 19 would be 3 5s, 4 ones. Okay. So just so you kind of see, it's a stacking system. That's how they work. Now, their place values also stack in the same way. Okay. Let me give you an example of a number written in stacked form, and it's base 20. Okay. So There it is. There's the number. Okay. So the bottom number is the ones place. The top number is the next place up, which in this case would be the 20s place. Okay. So what we're saying is that we have the number 1 in the 20s place plus the number 1 in the ones place, which comes out to the number 21. Okay, very exciting. Let's see it get a little bit more exciting. Let's say we have 1, 2, 3 lines and a dot, and then another dot and a line. Okay. So again, same idea. This is the ones place. This is the 20s place. Okay. So the number in the 20s place is, so 3 lines would be 15 plus 1 is 16 in the 20s place. And then that would be the number 5 plus 1, which is 6 in the ones place. Okay, so grabbing my calculator and calculating 16 times 20. I get 320 plus 6, so 326. All right. Now, there is one obnoxious thing about the Mayan number system. Okay, and I'm going to show it to you. So we have a 3-tiered number now. All right. Ones place at the bottom. 20's place above it. Now, this should be 20 squared. It should be 20 squared. The Mayans, however, did something weird. Instead of 20 squared, they did 20 times 18. Okay. Above that, if there was another number, it would be 20 squared times 18. Like they start going by 20s again after that. But they don't. And I'll explain in a second. Before I explain that, let's go ahead and calculate this number. Okay, so we have 7 in the 20 times 18 spot. We have, let's see, 12 in the 20 spot. And then we have 16 in the ones spot. Okay, so grab your calculator. I ended up with 2,776 when I calculated this one. Okay, now the reason they do the 20 times 18 has to do with the Mayan calendar. Okay, so they have a calendar, and that's like it's an 18-month calendar with 20 days or something like that, and that's why they do 20 times 18 instead of 20 squared. So the Mayans, sorry, let me make a note of this. Mayans don't have 20 squared, but use 20 times 18. Okay, so one more example like this just to kind of show it. Let's say we have 2, 3, 4, 1, 2, and oh, sorry, I'm sorry, I did that wrong. Just 2 dots on that. Okay, and then bread loaf, the 0, and last one. Okay, so let's build up. This is a ones. This is the 20s. This is the 20 times 18. This, and now they return to the 20s, 20 squared times 18. Okay, there we go. So what number is in the 20 squared slot? Well, that looks like a 9 to me. Here, I'm going to write it below. So 9 times 20 squared times 18 plus, okay, 2 in the 20 times 18 slot, 0 in the 20 slot, and 6 in the ones slot. Okay, go ahead, do that on your calculator. And I ended up getting 65,525. Okay. All right, let's go the other way just to make sure we get it. Let's say we want to represent the number 105. Okay, 105. So we need to figure out how many 20s go into 105. Oh, I'm sorry, 106. Wow, that's so funny. 106. I don't know why I said 105. 106. How many 20s go into 106? Okay, so 20 And that should be, oh, this is where I got the 5. 5 times 20 gives us 100, right? Okay. And then we want to add 6 more to that, which will be in the ones place. Okay. So to represent this as Mayan number system, you would do 5, which is a bar, and then 6 in the ones place. So 120. There you go. All right. Let's try one more. And we'll do a more complicated one. 2782. Okay, so 20 is probably not big enough. Grab your calculator. Let's calculate what 20 times 18 is. I got 360 for 20 times 18. So I'm going to try to do 360 instead. I want to see how many 360s there are. Okay, so let's see. I'm going to divide 2782 by 360. I get 7 point something. So I'm thinking there might be 7 360s here. Let's see. So 7 360s comes out to 2,520. Okay, that's definitely close to our number. Cool. There we go. Plus, okay, now let's figure out how many 20s are left. So I'm going to take this number and I'm going to do 2,782 minus this number. And I get 262. Okay, so how many 20s fit into 262? That would be 13 times 20. Yeah, 13 20s. I divided 262, by the way, by 20. Okay. So what I did on my calculator, just so you know, on my calculator off to the side, I started with subtracting 2782 minus 2520, and I got 262. All right. And then I went ahead and divided 262 by 20. And that got me 13 point something. And that's where I got the 13 from. Okay. So then I actually went ahead and figured out what 13 times 20 is, which is 260. So right now I have 25, 20 plus 260, and I'm just 2 numbers short now. So I need 2s in the ones place. And there we go. That'll add up. Okay. Now that I have all that I need, I'm going to go ahead and erase this, just the work I was doing on the calculator. I'm going to go ahead and write the number. Okay. So 7 is the first number. 13 is the next number. And then 2 is the last number. And there we go. That's how I'd write that in my enumeration.